All right, so let's get started. Welcome to my talk, Semi-Offline Attack on Android Full Disk Encryption. As Bruno just said, I studied almost with him at Royal Holloway. I think he graduated when I started, or almost. This is my Twitter handle for if you ever want to contact me, if you want to follow me. I'm not very active at the moment since I moved from being an external consultant to being a consultant in a corporate. So today I will talk about full disk encryption on mobile devices. I give you a short introduction into full disk encryption, then full disk encryption in Android, and then I will discuss 3 attacks. All 3 attacks are brute force attacks, and they follow the stupidest, simplest strategy that you can imagine. We start at pin 000 and run up to pin 999. The first one is the baseline attack, it's the online attack. Then we'll discuss the offline attack, and last but not least, my semi-offline attack. All the work is discussed in my master thesis. It's published on the website from the university. If you care to read 80 pages, feel free. So yeah, let's get started. Full disk encryption on mobile devices. What is the situation? When do we need or when do we want to have full disk encryption? You lose your device or somebody steals your device. You don't want them to be able to access your data, so you think about, hey, let's have full disk encryption. But full disk encryption is data at rest. So storage encryption only works when the device is at rest. And here's the first question for you guys. Who actually switches off the mobile device? Hands up. Well, last time at least one person put their hands up. Okay, so yeah, that's it. Basically, your full disk encryption is not really helping you because you never switch off your phone. So all that protects your data is your screen lock. That is the limitation number 1. Limitation number 2, when I steal your device, I have your device and I can do with it whatever I like. Yes, I know remote wipe exists. But guess what? My basement doesn't have cell phone reception, so your remote wipe is done again. So what are the elements that a full disk encryption needs? Obviously, we need a disk encryption key. In Android, they call it master key. And we need a cipher. Android uses AES CBC. And we need a procedure to do the encryption and decryption for us. That is Linux famous dencrypt. So those of you who know dencrypt know it is in fact a transparent encryption. That means as long as your device is running, your device is decrypted. Every read operation is decrypted, every write operation is encrypted. But AES has a 128-bit key, and I don't know, when I go to my mom or my grandma and tell them you have to remember 128-bit key, they think I'm nuts. And honestly, we would be nuts if we would try to remember 128 bits. I wouldn't even try. So we need something better to come up with a protection for our master key. And that's the key encryption key. Now, if you think that can be shorter than 128 bits, you're fooled. Because Android uses the key encryption key as a pure key hierarchy. It uses the KEK to encrypt the master key, again with AES CBC. So we don't really gain much by having a key encryption key because it's again 128 bits, otherwise the security of the master key would be lowered. That's fine, come in, have fun. What is the solution to that problem? The solution is a KDF. The user has a secret value, a password, and we apply the KDF to it in the sense that at the end we have a 128-bit strong encryption key. So let's have a look at all these different elements in a bit more detail. As I said, the cipher is AES. AES is a block cipher, 128-bit blocks. That means the plain text will be chopped up in 128 bits. We have 3 different key sizes available to us, 128, 192, and 256. Android uses 128. It needs block cipher mode. We have the choice between CBC and XTS. Standard is CBC. It's a traditional, well-known mode. We'll see that in the next slide. XDS is available in Android, but you have to sort of recompile the source code. Yeah, you're not going to do that because then every update you would have to do the same again. XDS is designed by EEE. It's a standard. It got some criticism because the standard is not open, so you have to pay a lot of money or a little money to actually access the standard, or you're a student at a university and your university has access to the standard for free. CBC. Hopefully everyone, if you have ever heard of CBC, because it's not really that new. It's A, used in encryption. B, CBC mode is also used for different crypto primitives. For example, CBC MAC. It offers message dependency. And good thing the room is smaller than the last time, because I think you can all see the graphics. We have plaintext 0, which is XORed with the initialization vector. Then we apply the encryption on it. Outcome is the first ciphertext block, and that one is fit back into the second plaintext block, and so on and so on. And now when you think about this, for storage encryption, that's not really ideal. You have your Tera storage disk, and you do that. That means you start at byte 0 and you end up somewhere in the end. But what if you want to change a file at the beginning of the disk? You would have to decrypt everything until you're at that position. You change the file and you re-encrypt. That's not really efficient. So they came up with another idea, and the idea is encrypted salt sector IVs. So now actually full disk encryption is not encrypting the full disk at once, but encrypting each sector individually. And we have a sector IV. So every sector gets a new IV based on the sector number and the key. So now when you have to write a new file, you just have to decrypt the sector, change the file, and re-encrypt the sector. Much better. So we are at the master key. In Android, master key is created with the create encrypted random key function. It's still in there, I just checked. What it does is, and that's actually quite funny, it reads twice 16 bytes, so that's 128 bits, from def u random. That's good. The first one is the key, the second one is the salt. Those keys never change until you wipe your phone. Now, if you work in a corporate and you have these nice policies, please change your password and keys every 60 days, you have a problem here. Because your users would have to wipe the device every 60 days. They're not going to do that. But you need to know that when you bring that in your environment, that this happens. So in your risk management, you have to accept the risk, or you really have to tell your users, hey, you have to wipe your phone every 2 months. As I said, it's protected by the KEK. And we look at the KDFs, the ones that help us not to remember 128-bit keys. Up until Android 4.4, Google used PBKDF2. It's also a known KDF. It has tweak values. It only focuses on being processor expensive. This is not a good thing to do today because, let's face it, CPU power is probably the cheapest power that you can get at the moment. So as of Android 4.4, they switched to script. Script is more than just processor expensive, it is also memory hard. And what that means is, for a normal task that you would assume, it takes up more memory and more processor power. For the user, during the entering of the pin, it's not a big disadvantage. He doesn't really feel it. But if you were running a brute force, you get it. It slows you down. Now, that's what's happening until Android 4.4.4. You had a pin, you had a password, you applied the KDF, you got the KEK. With the KEK, you decrypted the master key. With the decrypted master key, you decrypted the full disk encryption. But if we think about the term full disk encryption, it implies the full disk is encrypted, right? That is never true. At least you will always have something like the metadata partition, which is not encrypted. It stores all the crypto material that you use for the full disk encryption. So that is true for every notebook that's out of full disk encryption, as well as every smartphone. And in fact, when you look at the CDD document, which is a document that every Android version gets, you see there, encrypted is only the user data partition. And the user data partition is the /data mount point and the internal SD card. Which makes kind of sense, because why would you encrypt the system partition of an open source phone? Everyone knows what is in there. It's not really secret. And it's not bad either, because everything that you as a user store on your phone is stored on the user data partition. If it's an app, if it's a document, if it's a photo, it's there. So it's really good efficiency. So I run through the introduction. I hope you're all with me. We now start looking at the three different types of attacks. The first one is the online attack, and that one is quite obvious. So I also use it as a benchmark. The preconditions for the attack is you need to have the device. So I either steal it from you or you lose it. And I need it for as long as my attack takes. I need a script that I can run, or I need a physical attack machine like the one Engler and Vines demonstrated on DC21, which is kind of funny. It's one of these cool super robotics. So the problem is Google is not stupid, and thank you. So you have to enable ADB, and you have to trust the host, the attack host, to be actually able to do that from a locked smartphone. I did that. I trusted my host. I enabled ADB for good. And then I figured out, okay, what do I need? What can I use? Those are the two methods, input tap and input text. Tap is very slow. It's basically virtually tapping on the screen. And it's also cumbersome because the Nexus 4 has a smaller screen than the Nexus 6. So I had to remap out the screen, and basically mid doing that task, I thought, I'm looking for another alternative method. And that's input text. It's much quicker. And 10,000 pins took me 22 hours, 40 minutes. So that's my base level. Everything better than that is good. It triggered 2,000 timeouts. And speaking of timeouts, the countermeasures. Now, I said we use the KDF to get from a user-defined value to a bit key that then protects the master key. That's only true on the startup screen. So when you start up your Android phone, it asks you for the value. That's happening there. But you use the same value to unlock the screen every time you use your phone. And as you see in the table, there are different countermeasures to that. While in the startup, after 10 failed attempts, you wait 30 seconds, and you can do this 30 times until it wipes your phone. On the locked screen, you can do this practically forever. I did it 2,000 times and then didn't wipe anything. And that's a problem, because it weakens the screen. It makes it more attackable. So we could ask for them to bring us a wipe operation, let's say, after 1,000 failed attempts. I get it that we don't doing that. It's a bit stupid when you have a small kid and they always press on your phone and then it wipes your phone. You laughing? You know the story. So we could arguably say that's fine, but let's do a different thing. We could increase or decrease dynamically the penalty timeouts. Nevertheless, no one is as stupid in doing an online brute force attack on the screen, just as I did. Conclusion, the ADB is secured sufficiently enough. We have authentication, we have to enable it. Physical attack devices is quite complex. It took me almost a day to brute force these 10,000 pins, but there are some improvements. Now the offline attack, and I call it the old-fashioned way. So the preconditions change a little bit. Now I don't need to have access for the full attack time to your device, but I need access for as long as it takes to get these two partitions. Remember, that one stores your encrypted files and that one stores the crypto information for the full disk encryption. So that begs the question, how difficult is it to actually get two partitions off your device? Well, there are two scenarios. For me, as an attacker, the best case scenario, you have an unlocked bootloader. Who has an unlocked bootloader? Who likes to play around with Android phones? No one? One person, at least two. Good. So it's very easy there. All I have to do is start up my image or any recovery image, DD the partition, and send it to my host. Less good if you have a locked bootloader and you have ADB disabled. That means I have to unlock the bootloader, which triggers a user data wipe. But the thing is, when you read Simon and Anderson's research, the wipe operation of the Android manufacturers is sometimes pretty faulty. So it might be that you have some data residue. It might be that you have the full user data residue. And if you don't want to risk that, you just image it with JTAG. It's slow, it's cumbersome, it's error prone. Yes, it's possible. And even if you don't have JTAG or you don't want to do that, you can unsolder the chip. That's the attacker's last resort. He can always unsolder the chip. So there is another script that's initially written by Thomas Cannon and Satan Bradford from Wire Forensics. I think Wire Forensics is not on the market anymore. They were sold out. It ships with Santoku Linux. Right? Sold out. It ships with Santoku Linux. I didn't use their script. I used the version from Nikolai Alenkov. He's the author of Android Security Internals. Very nice person. I was in contact during my master thesis with him. Had some nice discussions. I used his script because he basically improved it a little bit. I liked it more, and I built up on that. It's handling only pin numbers. That's fine. My online script handled only pin numbers as well. And the procedure is very simple. We take a candidate pin, we apply the KDF, we decrypt the master key, we decrypt the header file, which is basically the beginning of the full disk encryption, the user data file, and then we check for the ext4 signature. That's the bit that I included in the script there, because initially the script only looked for 16 null bytes at the beginning of the ext4 partition table. That's fine, should always work, but you know, there is a magic signature number for a reason. We know it's ext4, so let's look for that as well. That's how you run the script, and that's how long it took for the same amount of pins to run. Remember before I said everything lower than 22 hours and 40 minutes is a win? That's a big win. That's less than an hour. So what are the countermeasures that we have for the offline attack? Well, we could try to prevent the user from imaging, or the attacker from imaging the partitions, but there is a problem with that, and I just told you that you can always unsolder the chip. It's complex, not everyone can do it, but still the possibility is there. So that's a lost race. We can try to make it harder to brute force it offline. And the only thing that helps us there is a strong KDF. That's why they moved away from PBKDF2 to script, from only being processor expensive to also be memory hard. But still, my offline attack with the 51 minutes, that run with script, not PBKDF2. So conclusion to that attack is we're much quicker, But we still miss some security controls. We need something to prevent that attack. And actually, Google thought we need something to prevent that attack. And they responded with improvements. They said they fixed it. And I like that. I like when people say I fixed it, because then I look at it. And I liked it especially because there was a time where James Comey said, oh, we're going dark. All the terrorists. It's really bad you do full disk encryption. So I wanted to look at it. And that's why my master's thesis was doing a security assessment of the full disk encryption. So what are the improvements that Google introduced? Well, they said they want to do a hardware binding of the crypto material used in the full disk encryption. But let's be precise, it's not the master key they bind to the hardware. There is still reading 16 bytes from def random. They bind the key encryption key to the hardware. And this is how it goes. That's the old process. We had PIN and password available to the user. We applied the KDF, and then we had the KEK. And you see the little gap there? That's the new one. So first of all, to notice, we have pattern. You can now use your pattern lock on the screen as well. And default password, and this is really the string that is used, default_password. It's written in the source code, by the way, so it's no secret. Why is that there, you may ask? So with Android 5 and the whole FBI we're going dark thing, Google also said, let's ship every Android 5 device with default full disk encryption. The problem is, when you switch on your device for the first time, it doesn't have any PIN or password or pattern set. But it needs it to start the encryption, and that's why there is a default password. And if ever you decide after Android 5 to remove your screen lock value, you divert back to default password. So if ever someone has a phone with no screen lock and you have access to it, it's very easy to find the master key. All you have to do is default password, script, and do the other thing down there. It's the known value, it's the easiest thing. But let's look what else is there. We still have script, the first KDF function. Then we get an intermediate key. That used to be the key encryption key before. And then we ask Android to sign it with the keymaster trustlet. The keymaster trustlet runs in the trusted execution environment of the processor. In Qualcomm, that is QSEE. So we bring the signature key material, which is also in the crypto footer, to the keymaster that is encrypted with the internal key from the keymaster, ask it to decrypt it, sign the intermediate key, and give me back the signature. So this is where the hardware binding happens. We have an internal keymaster key that encrypts the RSA key for the signature. After I have the signature back, we have to apply script again, and then we have the KEK. So from one KDF operation, we now have two, plus a public key operation. So the offline attack took 51 minutes. I expect at least 102 minutes. A little bit more, because we have the signing still there. So let's make it 110 minutes that the next attack should take. This is the offline attack. So when I drawed up this line before, I thought about, good, somehow there needs to be a way to attack it. And there really is. So this is the precondition for the offline attack. And this is the precondition for the semi-offline attack. So you might remember that's the same precondition. The yellow one is the same one from the online attack. We already had this. And it doesn't matter because I still have your device. You lost it. I stole it. I am in possession of your device. We still have to image the two partitions, right? It's semi-offline. And we still know how to do that. So now we don't just have an attack script. We have an attack client-server application. The server runs on the smartphone. It's based on CryptFSC. That's the main encryption functionality from Android. And the client is based on the offline attack script with added bits and bytes for the communication. So the server, the phone, really only has to sign the intermediate key and send it back to me. Receive, sign, send back. Receive, sign, send back. That's all it has to do. And I'm back in the game, if that works. So that's a communication. I have to initialize the key master, so I have to send the encrypted signature key. And then I can send intermediate keys, wait, test, and do that for as long as it takes until I finally found the right key. So let's take a step back. We have the device, we have an application, we have the partitions, and there is absolutely no reason why I should keep the phone in the state that you lost it or I stole it from you. I now have everything off the device and I can do with that whatever I like, so I wipe it. I get a new master key, that's fine, I don't care. I get a new RSA key pair, that's fine, I don't care. I send it over, I sent the old one over, I have it from the metadata partition. So that's how it works. We have to push the binary on the file, on the phone. We have to set up the communication between the phone and the attack host. We have to run the server, and we have to run the client. 2 hours, 8 minutes. I said 120. It's a bit more than 120. It's not bad. But let's take a look at a demo. It's the first time that I can do a demo. It's actually cool. So that's the server. It's already running, as you can see. That's the client. We don't see the full command. That's a bit bad, but sorry about that. So what it does, it sends over the key master key blob, and here it starts sending all the pins. As I said, it starts from 000, and this will now run for, I think, 3 minutes, and for as long we just continue. Where do we have that? And we come back to that later. So you might remember end of June there was this blog post from Gal, Bits Please, and he found some exploits in the trusted execution environment kernel. And he was able to read out the internal key master key. And that's pretty cool. I didn't have the knowledge nor the capability to do that during my master thesis, so I was really thrilled when I saw that. Because basically what that means is, instead of sending over every pin and asking for a signature, I only have to send back the key from the phone to the attack host, and then I can run everything offline again. It's still a semi-offline attack. All that changes is the attack bit on the phone. It doesn't have to sign it, it just has to give me the key, and then I can run both KDF application and the RSA application on my attack host. So what are the countermeasures? Still all the countermeasures from the offline attack before apply here. We can enforce locked bootloaders, because in the CDD, that's really not mentioned. Every manufacturer can ship a device with an unlocked bootloader. Hello Samsung Galaxy S2. We love it, it's good for us to play around, it's easy for us to play around, but it's not really good. We can remove the JTAG interface. I have lots of friends who would hate that because they play around with the JTAG interface on the smartphone. And it still gives us the option of unsoldering the chip. We can implement a key change mechanism for the keymaster internal key. That's actually something I discussed with Google back in 2015 when I sent them over my master thesis. And we thought about when you do that. So when you do that, you either have to brute force the 60-byte AES key, have fun with that, or you have to solve the RSA problem or brute force the RSA key. But the real question is, when do we change the keymaster key? Is it on wipe? So then I read out the partitions with JTAG and write back with JTAG. I never wipe. So the keymaster key would always be there. So when we conclude the attack, Google said they fixed the brute force offline attack. And yes, they did. Technically. They didn't. Because the problem was they had the conditions wrong. I am in possession of your device and I can do with it whatever I like when I have the partitions off the device. They forgot about that. They worked on improvements, is the more correct way actually to say it. And the improvement is released in Android 7, file-based encryption. So remember when I said if you never shut down your phone, your full disk encryption is a waste of your power? That changes now with file-based encryption. All my work was based on Android 5. During my discussion with Google, they said it should also work on Android 6. After the first talk that I gave in June, I promised Bruno to work in a proof of concept for Android 6, and I miserably failed because I didn't have enough time. So Google believes my attack would work on Android 6. I trust them. I say we have 34% of smartphones running Android 5. We have 28% of smartphones running Android 6. So at least I know for 34% the attack still works. For 28 I have to say, yeah, probably yes. And Android 7 is only at 0.3% distribution at the moment. So not really lots of people have this countermeasure. So before we actually look at this, let's see if we were successful. So that's the server. That's the client. As you can see, my pin, and indeed it was 0099 for that time. That's my pin. That used to be my master key. I wiped it since then, so have fun writing it down and taking a picture of it. It took us 128 seconds. We were running a presentation next to it, so it works around fine. We were successful. And the good thing for me is it didn't take me more than 22 hours. And it didn't take me much longer than the offline attack. Because remember, we doubled the KDF applications and we have RSA signature operation on it. Plus the communication overhead. Thinking about that, I must say I'm probably as efficient as the offline attack with the semi-offline attack. Yes, the attack is a bit more complex, but still, I think it's quite good. And that's it. I was very fast today. Any questions? Sorry, yes. Wait the mic, so everyone can hear you.
So, if I understood well, your attack is a brute force attack on the pin of the phone, right?
Yes.
So what if we increase the size of the password that we use? Wouldn't that also be a countermeasure to perform the attack?
Of course, yes, it does.
And I think that should be the first thing that they should think about before trying to do two KDFs and sign the key, and maybe that's a easier solution, no?
It's a good question. I've never really figured out why they did two KDFs, but it wasn't to really slow it down. I think it has to do when you look at what you receive as an output from the RSA signature to really ensure that you get the same as you had before. I totally agree with you. Yes, make the password more complex, but then again, it's a smartphone. How complex should a password be for a smartphone?
It's a trade-off, right? Yeah. Between usability and...
Exactly. The pin obviously was just here for benchmarking. It's the easiest thing to do. You only have to run through 10,000 numbers. So for the research, it's fair enough. I agree and I get this a lot. But then really, I have a company and we set out a policy to have a complex password for your smartphone. And every time when I enter an office as a security officer and security consultant, I get shouted at because of that policy, because people hate it. It's very cumbersome to enter a complex password on your smartphone. We could also argue you could have a separate password for the full disk encryption than you have for your device unlock, for the screen unlock. But then when we see how many people actually switch off the device, probably everyone would forget the very complex disk encryption password. But I absolutely agree. We need to get the users to pick a complex password. The strength at the end is the password complexity.
Is the fingerprint authentication just making it a much more complex user password? Or is that, and do you understand?
No,
how
I wouldn't
the key
say
length for
so.
that?
Because actually what happens when you do a fingerprint, when you use a fingerprint reader, it reads out all the properties of your thumbprint, and then it stores it as a bitmap. So you have a series of bits and bytes that represent your fingerprint. Yes, it will be longer. I think in iPhone it's over 2048 bits long. It's harder to brute force, yes.
Okay.
But it's not really a solution when you see that you can circumvent the fingerprint reader with a gummy bear.
Okay.
Someone else?
Those benchmarks results were for the worst case scenario, right?
Yes,
Where
9999.
my pin would be 999, right?
Yeah, okay. Exactly. That's why I said run through 10,000 pins.
Yeah. So if I were to make your life a little bit harder, I should set my pin to 999, so it would take you more time, right?
No, because if I said it's a quite stupid strategy to run from 00 to 999, okay. Because in fact, you would use in such a scenario when you have only 4-digit pins, you would start to look at pin distribution. What are people using the most? So first off, I would start with every pin 1950 or 40 to 2010, because people love to use their birth year as pin. I had one example in it. I took it out for this talk today where it was indeed my birth year as an example, because I wanted to look how long does it take. And in my thesis, you can actually see the results for how long it takes to brute force 1986. So that's not a good idea. But when I think about these people. So first of all, you would do you take the birth years, and then you take all the 00, then you take all the patterns on the screen. And then you probably start from the top and from the bottom. So when someone has to pin 5,000, you hit them in half of the time anyhow.
Okay, great.
It's all about the strategy.
I was wondering about that. If you studied how people input their codes.
No, I did not look at that specifically.
Have you thought about parallelizing your attack? Using distributed
I think you should use the microphone, so that is also...
Have you thought about parallelizing your attack? For instance, using some kind of distributed strategy to accelerate actually the brute force attack?
Not during the master thesis, but yes, indeed. To speed it up, parallelizing is one of the things. I mean, it's all serial now. So I take one pin, I apply the KDF and send it over. I could send over bunches of signatures and get bunches of signatures back, or use several threads to do the job for me. Or as in Zurich, a guy actually proposed, how about we apply the KDF and store all the data first and then send everything over all the time to the device. So it's about time memory trade-off, where you basically come in there. So you can calculate all the values, all the KDF values of all the pins first, and then you send them over, but you need a lot of memory to do that, to store all the values first. So as I said, it's really keep it simple to be able to compare the different types of attacks. But absolutely, if you parallelize it, you're much quicker. Okay, I think that's it then. Thank you very much for having me.